Good morning, students. You know, Professor Ron is enjoying the cool weather. I made a comment about that yesterday, and don't know how long it's going to last, but certainly running in the cool weather is always a treat. It's like, you know, holidays come early when we have that. After the Christmas holiday, I'm going to spend some time in Montana, where it really is cold, for about a week with my sister and her family. And so maybe I'll get used to that. If we get a little cold weather now, it won't be such of a shock. But I'm happy to have some cooler weather. I think that it just keeps us alive and reminds us that things are going to get better eventually. Now, I wanted to let you know that what we cover through today will just be some topics on parabolas and ellipses, just two types of conic sections. And then at the first part of next week, we'll have our fourth test. I'll put up a announcement about that. That way we can have a test with less material, get it out of the way before the time that you have off for your break. Unfortunately, school must go on, but I don't want to crowd the time that we have when you get back, excuse me, with a fourth test and your final exam. That would just be too much. So I thought about this for quite a long time, you know, over the weekend, and decided that a little bit shorter test would be good at the first part of the week to give you a 2-day window for that. So I'll have more information up about that. But of course, that'll just cover the remainder of the trig and just a couple of new topics we do today. I think you'll find the conic sections very interesting and probably not as difficult as the trigonometry, and maybe something you thought about before in a previous algebra class. So before I actually do that, I just want to do one preliminary exercise. I had several questions yesterday about trigonometry, and in the afternoon I had a question about a trig equation that actually turned out to be very simple, but I just want to show you an example of how you can use your trig identities to solve equations. So let me share my screen with you. Just remember that everything that you have learned in trigonometry is valid. Just because you have a new identity doesn't mean that you just have to focus on that identity. Use what you know and make the problem as simple as possible. Now, the student asked about this particular question, and it just basically said solve. It didn't say solve for all solutions, but again, we know if we solve for all solutions, we can limit them to a particular interval. But it said solve in basically the unit circle, 0 to 2 pi. And the equation was very simple, all in first degree, and it looked like this. Theta, tangent of the half angle, minus sine of theta. Now, of course, last week we did factoring, we used Professor Ron's lemma, we used sum to product to get the zero product law. For instance, if we can use the zero product, then that really covers everything for us. And those are the techniques we used in the college algebra review. But in order to do this, we want to be able to have some common factors here. So that remarkable formula, the one that you use, for instance, when you do half angle problems, you look for the cosine and sine first, then you get the tangent by taking ratios. So don't forget that good hint. But we can use the tangent of the half angle, which we derived, which is sine theta divided by 1 plus cosine theta. So this is a remarkable formula, and I will just say this: no matter how you solve an equation, if your mathematics is legitimate, then the results will be the same, regardless of the technique. But again, this is set up primarily to have you use this. So now if we make a substitution, we can easily factor and then just do some very simple algebra. So at this point, we see we have a common factor of sine, which we can factor. And then we have very simple algebra inside just getting a common denominator. Now I'm going to go ahead and not put the 0 here and simplify this by just getting a common denominator. You see what we're going to get. For instance, here we'll have the sine theta, and then with the common denominator of 1 plus cosine theta. So then, of course, we'll distribute the negative throughout the 1 and the cosine. Of course, the negative ones absorb, and then we have a negative cosine. So this will be a negative sine theta, cosine theta, divided by 1 plus cosine theta equals 0. So when we look at this and we think about what we're trying to do as far as solve this equation, we can find zeros here, and then we can look back up here to make sure that everything we have up here works. So you're thinking, okay, well, we've done some algebra, kind of like squaring, and so have we introduced extraneous zeros? Well, we have that possibility is certainly on the table. So what I'm going to do is just remind us, this is where we started. So any value that we determine for theta must solve this equation, and it must make sense. It must be defined clearly. That we get implicitly. So now by zero product, that would just, the negative doesn't matter. We would have sine theta 0 or cosine theta. So these are quadrantal. These are like on the axes. So we like these problems. They don't take any time to do. Let me write this factor as cosine. We don't need two sines. I thought this was an interesting problem. Not very difficult, but very interesting. So now when we look at sine theta equals 0, we know those are just multiples of pi as we bump back and forth along the x-axis. So if we're thinking this range here, we get a 0 and we get a pi. So the multiples of pi that would lie in here would be these. And then of course, if we go up here, tangent of 0 is 0, sine is defined for everything. And then if we look here, so I'll put a check here, but when we do pi over 2, x equal pi over 2 is a vertical asymptote of tangent. So we can't substitute the pi here and get something that's defined. So in this case, by checking the original, we discard. So when we check the original equation, this makes no sense. So we can't use that. So that's extraneous. Now here, what about the cosine? Well, that's on the y-axis, pi over 2, 3 pi over 2. And those live in here. So you didn't, you basically would just have odd multiples of pi over 2. So this is work we did last week. And so all of that is still in play. But now when we substitute, we don't have to worry about sine. It's defined for any real number. But here we get a pi over 4 and then a 3 pi over 4 when we divide by 2. So both of these are good. Okay, so now when we write our solution, we have 0, we have pi over 2, and we have 3 pi over 2. So this is one of those problems where you're grateful, and we did one of these last week, you're grateful that you found a solution, but you don't want to be too overzealous. We always think, okay, we've got values for X, we're in college algebra or whatever, and we're like, okay, done all we need to do. But if we introduce new expressions in the variable, as we've done here, or if we introduce a squaring mechanism, we found that that can introduce solutions that will solve this equation, but not the original. So that's what's called an implicit equation. And we like implicit equations. The conic sections will be implicit equations when we get to the ellipse, like a circle. And so we're grateful for what we have, but we have to be skeptical at times. So think about this when you're doing your problems, and you try out an answer, and I think what the student had done is that they they had the pi in there, and of course they weren't getting a correct answer. But then a little more looking at it, and I was grateful that the student had worked it out, because it was easy to check to see that this did not work. But the idea is that coming up with this makes very good use of this remarkable formula here. So remember, when you solve the trig equations, there is no one way to do them, but there's usually a way that seems to be a little bit more straightforward. So don't just look at something and say, well, I'm not sure about that, or I'm not sure what I want to do. But I will say this: what we want to do is be able to have at least the zero product. And then, of course, we want the variable to be the same. We've got a half angle here and a single angle here. And so that we've got to change that up. And this satisfies that quickly. So I thought this was an excellent example that I would share with you. Okay, so let's get back to the real world and the conic sections. So that was our preliminary, just because as we do problems, as I do problems in conference hours, I keep track of things that might be different, or that utilize maybe a technique that I talked about in lecture, but maybe didn't say a whole lot about. And I thought that was a unique problem. Now, I want to say something. I've written up a nice little sheet here about the parabola. Before I show it with you, I just want to remind you, why do we call certain curves conic sections? When you think of the double cone, for instance, the double nap cone, when you take calculus 3, you'll talk about the double nap cone. The cone itself is just this object that's three-dimensional, two-dimensional surface, but three-dimensional. And then you can double it. You can just repeat. That's what the double nap cone. And so when you actually think about this in terms of a quadric surface, when you take Cal 3, this is an elegant course. I've designed an honors course for this, as I did all the math classes, and it's a fun class. And when we look at this particular function, it's defined this way. So this is a quadric surface. Now, again, you're going to talk more in detail when you take Cal 3. But when we talk about a conic section, we talk about planes intersecting the double cone, or even one nap of the cone. So if we just basically look at one nap here and intersect with a cone, with the cone with a plane. So we intersect with a plane. When we look at the cross section here, we get what looks to be a quadratic, something like that. So we call this a conic section, because as we intersect a single cone or a single nap of the double cone with a plane, we generate this kind of curve. And this is what we call a parabola. Now, you're thinking, that just looks like the shape of the graph of a quadratic function. Are they the same? And the answer is yes, they are the same. the thing is that now the Greeks were the first to actually come up with the conic sections. The Greeks were great geometers, and all of what they did, preceded Rene Descartes and analytic geometry. They just came up with this with their genius minds and their intuition about geometry. And so we actually get to the conic section in a way that's completely different from the way we talk about it. Now, this is fine when you think about a section of a cone, but we like to talk about things in terms of analytic geometry. That is, we like to combine the geometry with the algebra, like Rene Descartes did when he said, okay, here's the XY plane, let's coordinatize everything so that now we can talk about the parabola in an algebraic way. So here's the first conic section. Now the other section, we can take a plane, well, I can just use this color for a cone, lower nap, something like this. Now, of course, we could create a circle or an oval, but in general, we get what we call an ellipse. You get something like that. This is called an ellipse. Now, again, this is what we call a conic section. And you're thinking, well, Professor Ron, if you angle this so that this plane is perpendicular to the axis of a cone, that oval becomes a circle. So you're thinking this is just really a generalization of the circle. And so if we come up with an algebraic manifestation of this, will it look like the equation of a circle? And it will. If we come up with an algebraic manifestation of this, will it look quadratic like we did in college algebra? The answer is yes. However, now we're not just going to have parabolas that open upward and downward. They're going to open to the right and also to the left because we're not necessarily creating a function in X. So everything that we would expect here algebraically, we will find is true. But just think, this is why you call these particular curves conic sections. There is a reason behind this. Students will often just, repeat these buzz phrases and oh, we're studying conic sections. Well, why do you call it that? Well, I don't know. It's parabolas, ellipses, hyperbolas kind of thing. So there is a reason behind the phrasing that we have here. So let's look at some of the algebra of the parabola. And this is where I've drawn a nice chart here to help you understand this. Now, what I wanted to do was organize everything in a way that gives you a good algebraic feel. Now, when we think of intersecting one nap of the cone with a plane to create a parabola, there is one other ingredient that we need if we want to make it algebraic. So what we do is we have a analytic geometry definition, and it goes like this. A parabola is the set of points in the plane equidistant from a fixed point and a fixed line. And you're thinking, how does that work? Okay, well, see, this is the analytic geometry part. So I wanted to give you an idea of why we call it a conic section, but now we kind of divorce ourselves from that and think about it algebraically. So we still get the same shape, but here's what we do. This is what Rene Descartes invented, the Cartesian coordinate plane. So what we're going to do is say, this is actually what we're going to call the vertex. But to make this simple, we take a P that's non-zero and we set up the focus here at the point 0P. And you're thinking, well, Professor Ron, you're choosing the y-axis to place the focus. And it doesn't matter. We're going to see that we could put the focus on the x-axis and switch the x and y and get another set of equivalent equations, but then right and left. So that'll be easy. That'll be an easy switch. So we think, okay, in this fixed line, what are we going to call this fixed point? Well, I'm calling it, and it's standard, it's going to be called the focus. And the fixed line, this is a very old term, is going to be called the directrix. And so we think, okay, what's the simplest way to satisfy this condition with just one point? So we're going to take a point right here and make sure that it's the same distance from the focus and the directrix. So here's what we're going to do. We're going to be really cheap here. We're going to define the focus to be the point 0p for p non-zero, so p can be positive or negative. And then we're going to go on the opposite side. We're going to reflect this point in the x-axis and draw the horizontal line y equal the additive inverse of p. So we do an x-axis reflection. And so we're thinking, okay, well, now I look at these two distances here and they're congruent. So that point right there, the origin, would be a point on the parabola that we're describing, because it would be equidistant from the fixed point, the focus, and equidistant from the directrix, the fixed line. And you're thinking, okay, well, we have one point. Do we have to do a little more? Of course, throw in a little humor there. The idea is we just continue this. We say, okay, if this gives us a setup, how can we generate other points? So we just get creative here. We think, okay, well, we know that the parabola is a conic section and it has that nice U shape. So we think, okay, well, if we move up this way in the U shape, and then we try to fit it so that we've got another point here that's equidistant from the focus and the directrix. Remember, when we're distance from a line is always the perpendicular distance, otherwise we wouldn't know how to use it. We've got to have a convention there. And so we're thinking, as if we continue what we think to be the shape, another point, arbitrary p with coordinates x and y, like we're on the unit circle, would be addressed this way, where we have p the same distance from the focus as it is from the directrix. Now we're thinking, okay, the focus has coordinates 0, p. The point p has coordinates x and y. And then, of course, if we take this point here on the directrix, it have the same x coordinate, but it would have the negative p as the y coordinate, which defines the directrix. So, of course, this is easy. This derivation is simple. The one for the ellipse is not as easy, but it's certainly doable. So then we think we can use Euclidean distance, and we can use the square here because we don't need the radicals. That's just in the way. We've done this argument before. So we're thinking the distance between P and F squared would be the distance between P, and I call this point D for directrix. So you could label that any way you would like. So how do we do this? Well, we just take the difference between the x coordinates and square. So x minus 0 squared is x squared, and y minus p quantity squared takes care of this side right here. And then we do the same here. Well, notice I went ahead and wrote this in. We have x minus x. That's just going to be x minus x quantity squared. That's going to be a 0 term. And then we have y minus a negative p. So that'll be y plus p quantity squared. So we're doing the difference between the x coordinates squared plus the difference between the y coordinates squared, as we do in Euclidean distance. Now, you're thinking, okay, binomial, simple binomials, let's just see what we have. So here we have an x squared, so now we get y squared minus 2py, that is the product hit with the 2, and then the p squared. And on this side, similarly, we get the y squared, the y times the p times the 2 plus the p squared. And now we're thinking, okay, you know how Professor Ron absorbs things. You can put boxes around them or underline them. Don't use slash lines. That's not what I like. And I don't want to ever see that on your paper. I saw that on some of the papers in the work, and I don't want to see that again because that's not how I've taught you. And it's just poor notation. And you can quote me on that because it is. So here, this way, we can note the fact that these absorb, but we don't obscure the mathematics. So the y squareds absorb and the p squares absorb. And what's left is just pretty much, very little. Notice here that minus 2p can go over here and join the other copy of 2p to give us 4py. And then, of course, the x squared is by itself. So you can write these either way. You can write it in this order or this order. It doesn't matter. But notice that with what we've set up here, that this will either open upward or downward dependent on the sign of P. So here, when P is actually positive, we see that we have upward opening of the parabola just by our convention. And of course, if we had started down here with the focus, then we would have opening this way. So the P here, the sign is a dead giveaway, just like when you were doing quadratic functions in college algebra. Now, so we think, okay, this defines the conic section, the parabola, when we set it up this way. Basically, what we're thinking of is just like with the quadratic function, we have this point, which turns out in this case to define the minimum. And we call that the vertex. This is what we call the vertex. Same as we did before, the vertex. But we get it through different means, not through the way we actually derive the quadratic function formula in college algebra and pre-cal. So I can go ahead and define the vertex as the origin. That's always going to be the case until we translate it. And then, of course, we have the focus, which we've defined here. And then we have the directrix, which we've defined here. So all of this we already knew. We're just summarizing it. We didn't know that. Now the nice thing about this is that when we see an equation that has this form, we can figure out the P, because we know that if we isolate the x squared, then the result will be 4py. And whatever coefficient we have of y, that will be equal to the 4p. And then we'll be able to move the problem forward. So this is essential. This is like doing identities in trigonometry. This equation defines the parabola, okay? And now there's one other piece of information here. Of course, we have an axis of symmetry, which I wrote here. That's not going to change. X equals 0. And then, of course, if we were opening right or left, we have y equals 0. But the thing about this is that there is one aspect of this which we call the focal diameter. And this is, again, something that the Greeks came up with. So if we look at our quadratic here, it's a quadratic function. We see it's now quadratic, so we can call it quadratic. We look at the parabola and we look at the focus, and we just take the line that crosses the focus parallel to the directrix this way to intersect the parabola. Okay, well, of course, that's going to be, what is it going to be? Well, notice we have a point on the parabola. And so if we go this distance, we have a P and a P, that's a 2P. And then if we go this distance, that's a 2P. So the idea is that by definition, this point would have to be 2P comma P. Likewise, I can go ahead and fill this in. This point would have to be negative 2P comma P. Now, why is that important? Well, that kind of gives us a freebie to get 2 extra points on the graph of the parabola. So what we're seeing here is P could be negative. So we don't want to define a distance with P by itself. We want to define it with its absolute value. So notice this distance from here to here will be 2p, and the likewise distance over here will be 2p. The complete distance will be 4p if p is positive. So to counter all of that, we just say 4 times the absolute value of p will be this distance in any case. So we call that the focal diameter. Now, you can write the focal diameter as 4 times the absolute value of p, or you can just slap it, the absolute value on the outside, if that's easier to write. It won't make any difference. So we're thinking the focal diameter is just an extra piece of description that again, I remember I had a student one time, it's like, oh, I see, Professor Ron, the focal diameter can help us get some additional points without having to work too hard. And I said, that's an excellent observation. And it is. This student now has graduated from Texas A&M and is a mechanical engineer. So I guess he put that mathematics to good work. Or to good use. So I think that the idea here is that we have a simple summary, and then we can think about just transferring this in the right and left direction. So let's do that. So let's take everything we have and think of the same picture going in the other direction. So let's go ahead and draw that. So we're just going to switch everything. So now we'll say switch X and Y. So maybe, you know, we'll just have it opening to the right, either way. So maybe when we started out this process, you're thinking, do we have to do everything over again? No, we'll use the symmetry. So maybe we started out, instead of putting the focus on the y-axis, we put it on the x-axis, and so we just get focus p comma 0 right there. And then the directrix will be here. So now the directrix is a vertical line. So this will be x equal the additive inverse of p. And now, of course, the vertex is still at the origin right there. And then we can draw I'm not really kind of keeping this too much to scale. I'm making it big enough so you can see it. So now we could have a parabola that just opens to the right or the left. And then, of course, we can do the same thing. We can shoot a line right through the focus, parallel to the directrix, and get the focal diameter. So we'll say 4 times the absolute value of p, or just put it on 4p is fine. This will be the focal diameter. So now you're thinking, okay, well, so what's the equation look like? So now it would be y squared equals 4px. Switch the x and the y. So we don't have to do everything over. We just switch the x and the y because we know we're lazy mathematicians. And so that's what we do. We prove it, and then we use that proof to give us this situation. And so now if we put all this down, we got the focus on the x-axis, and then the directrix is right here. So switching the x's and the y's, switching the x's and the y's where the coordinates are concerned, and switching the x's and y's in the equations. And then, of course, the focal diameter does not change. So you can do 4 times the absolute value of p, or you can just slap it on the outside like that. And then, of course, now when we look at this, the axis of symmetry will be the x-axis. So we can think of y equals 0 as an axis of symmetry. Now, the only thing that would be left here, ladies and gentlemen, is there. And if we have time at the end of class, I may talk about rotation of axes, but we can translate the vertex. You're thinking just like we did in college algebra in the pre-cal first part, the review of that. We could translate the x by some units h and translate the y by some units k, just like we did with the college algebra transformations, and do the same here and move the vertex to another point and basically see how that changes the shape of the equation. Well, algebraically, it's very easy to do that, but maybe we get an equation that's in a terrible form, that's not, the square's not completed. So we complete the square, and then it's like working with the circle all over again. So that will be the next level that we'll do at our next lecture. But for right now, we just need to get used to this. So that'll come. But if we have time at the end of the class, I will say something about rotation of axes. That's a more advanced topic, but it is an interesting topic, and it uses trig. And since you know trig, we could talk about that, but I'll just have to see how the time works out. So now what we see is that as we compare the two, upward or downward, right or left. And this is the key right here. Now, what I like about Dr. Stewart is that he takes full advantage of the focal diameter, and we're going to do that too. So let's look at some simple exercises with this. Again, when we think about what we're doing with the conic sections, this is more similar to what we were doing with just basic ideas in college algebra. So this is refreshing and maybe not so difficult. So here's an example. What we want to do is write down all the particulars write down the vertex, write down the focus, the directrix, and the focal diameter. So here's an example. So we have the equation x equals negative 2y squared. Okay, so the idea, when we look here, we're thinking, well, this is a parabola, but the y squared term, it appears to be squared, or the y appears to be squared, and then we've got this negative hanging out. So we're thinking it's probably going to open over to the left. But first, when we look at this, we recall the standard equation. That is what we wrote on our last sheet. We have y squared equals 4px. So that's the standard equation, which defines the p, and we need p. So now, equivalently, we have y squared, just divide by negative 2, will give us a negative 1/2 x. Okay, so at this point, we're in very good shape. Notice this implies 4p equals negative 1/2. So equivalent, so this implies what? The focal diameter is the absolute value of negative 1/2, which is 1/2. That's the focal diameter. So we get that for free just by having 4p. But now also this implies if we divide by 4, p equals negative 1/8. So now we can see parabola opens to left. So now we got the focal diameter. We can go ahead and summarize. We have the vertex. It's always going to be 0, 0 unless it's translated. We have the focus, which will now be p comma 0. So we have negative 1/8, 0. And then the directrix will be the vertical line, x equal the additive inverse of p. So if and only if x equals 1/8. And I'll go ahead and repeat the focal diameter, 1/2. So this pretty much defines this conic section, the parabola. Focus on the x-axis, -180. The directrix, x equal 1/8. The focal diameter, 1/2, excuse me, and the vertex at the origin. So we can get a nice sketch of this. Now notice, you're thinking the focal diameter is 4p, and so if you cut that in half, you get 1/4. And so that would be a simple way to go ahead and get a free point. Okay, so let's go ahead and just do an inexpensive sketch. Now, of course, we've got all these fractions, so we'll spread things out. Just remember with the scale, that's going to make your graph look a little bit different, but you don't want the scale so small that you can't see your points. So we'll spread things out a little bit. So now notice, and this is important here, this is opening out to the left, so we can, at this point, when we look here, for instance, let's see here, let's think about 1/2 of the focal diameter. That equals 1/2 times 1/2, which is 1/4. So we could move up, in this case, from the focus up a quarter and down a quarter. So when we think of that, so we get like, we'll just say, let me just call these new points. So we can move up, so we're going to get -1/8, comma 1/4, or 2/8 if you want to write it that way. And we'll get -1/8, -1/4. And that'll give us 2 new points just using the focal diameter. So now let's spread things out a little bit. So we'll say about 1/8, -1/8, +1/8. So we'll say negative. Let me just label the point instead of trying to put the, so here's our focus. I'll do it over here to get out of the way of the points that I'm going to draw. So that's -1/8, 0. And then our directrix here. Yeah, I put that a little bit close. So let me move that over a little bit. Out right there. So this is just a little picture of what's going on. This is just icing on the cake, so to speak. So we get x equal 1/8. We have our vertex right here, B 0, 0, our vertex. And then we can do our new points. So we'll do like 1/8, 2/8, -1/8, -2/8. So we get 2 new points, one here and one here. So we found those out using the focal diameter, which is a whole lot easier than trying to work it out that way, picking an x and trying to solve for y or vice versa. This is like really simple. So it's a really nice way to use the focal diameter. So we have what, -1/8, comma 1/4 right there. And this point, I'll just put it inside. We'll have -1/8, -1/4. So we can just connect here. Like that. So there's an inexpensive drawing, or if we're in for Great Britain, drawing of our parabola using 2 inexpensive points and the vertex. So when you graph these in WebAssign, you'll probably need at least 3 points, and you can get 3 easily. The vertex 0, 0, because it won't be translated yet, and then of course you can use the focal diameter to get 2 more, and that'll probably be more than sufficient if they're just asking for 3. But the beauty of this is that the focal diameter when you cut it in half, remember all the way across is 1/2. So if we cut that in half from the focus, we can go up 1/4 units and down 1/4 units, taking half of this to get 2 free points. So it's really easy. So we're basically just getting, if you look here, P 2P and then P negative 2P. Okay, so it's real simple, but I don't want you to have to memorize so many formulas. Just kind of think of it this way, and you can always easily generate points in kind of a visual way, or as I've done here, in a analytic way. So what we're seeing here is that this is actually giving us a little bit additional information, because when you look at this, if you're in your college algebra class, you see that this is not a function. For instance, if we look at this as a function of y, which it is, if we think of f of y equals x, then we see that we're duplicating things. The output, if we have an input of negative 1/8, we're getting 2 different outputs, and that's not a function. So you can break this up into 2 functions with the square root property. So for instance, if you've got this here, when you think about this particular setup here, then you're looking at saying, oh, I can use the square root property. So by here, equivalently, we would say that y equals plus or minus the square root of, and we'll just put the negative here, negative x over 2. And so this will define, the positive will define this branch, and the negative will define this branch. Now, of course, when you look at this, you see what the domain is. This would have to be negative real numbers, so this square root is defined. So now we can see that the domain here will be negative real numbers, including 0. So again, we think about having a positive arc and a negative arc. So this is one nice thing that this helps us with. We can say this arc is just y equals the square root of negative x. Well, let me write that a little bit bigger so you can see it. Square root of negative x over 2. And this one below will be y equals the additive inverse of the square root of negative x over 2. So that just gives you a little bit more utility with working with the algebra. And nothing new, you already know the square root property. It's just now that if we want to define a function here, we have to break it up into 2 pieces. This being one function and this being another function, okay? Because again, when you think about the definition of a function, we would have to do that. So that's just a little extra that you already know about. And for all practical purposes, it makes the use of the conic section more generalized, more generalized view of quadratics. And what we're going to see is that all the conic sections are quadratic in their algebraic manifestation. So that's a sigh of relief. Now, there's one example I want to do, finding the vertex and finding all of that stuff, and that's easy. That's just using the equations. But what Dr. Stewart will do is he'll change it up a little bit and say, find the equation of the parabola with this information. So let's do this one. Here's an example. So it says, in this case, the vertex is 0, 0. The focus is -1 over 24, 0. That's what's given. The vertex is 0, 0, and the focus, well, that looks familiar, is on the x-axis. And then it says, determine equation of the parabola? Well, when we think about this and we think about the fact, what do we need? You know, the P is kind of the premier thing. You know, get that P, then we've got that unique equation, so to speak, because that's the only parameter that we used when we were looking at these particular conic sec or this conic section algebraically. So now we know in this case f p0 is equivalent to saying p equals -1 over 24. So when we look at that, we're thinking, oh, okay. Now what we're seeing is that the P is negative, so this is going to open to the left. We're not asked about that, but we know it's going to open to the left just like the last one. So then 4P will just be 4 times -1 over 24. I know this is easy, but it's certainly interesting now that we can do this. So this will be a -4 over 24. So that gives us a -1/6. So our equation in this case, when P is on the x-axis, we have y squared equals 4px. So this is really simple. So this is really the key here. So now we have y squared equals -1/6 x. So the nice part about what we're doing now is that we have a more general view of the quadratic function that is in x squared and in y squared. And we can just play the little game here. So what we're seeing is that that 4p is the key. The 4p is the key. So if we're given p with the focus or the directrix, I mean, of course, now we know what the direct, we'll just write it down. The directrix is going to be what? X equals the additive inverse of -1 over 24, or this is even a worse scale, even more crunched up than the last one, okay? So there's our directrix. So what we're seeing here is that this P gives us the unique parabola. So now we can look back at other quadratic functions and now think about P, and it kind of changes our worldview of quadratic functions. So again, the P, the 4P helps give you the equation of the parabola. The 4P in absolute value gives you the focal diameter, which can give you 2 additional points. I mean, there's a very, very elegant simplicity about the parabola if we think of it in terms of analytic geometry. So there you go. So not as hard as the sines and cosines, but still interesting. And things that we'll actually use. So don't just look at this as being fluff. It's more than fluff. You get a conic section when you least expect it, and then you're glad that you did some work in pre-cal. Now, what I want to do with the second conic section is talk about it just like we did before. We know the second one is the ellipse or the oval. And so what we want to do is think about how can we define this in an analytic geometric way that will allow us to come up with a nice equation like we have for the parabola. And if we do it this way, do we get an equation that looks like that of a circle? And of course the answer is going to be yes, but we need to kind of figure that out. So let's look at the ellipse. So now an ellipse, we'll have a similar equation or similar definition. An ellipse is the set of points. So let's go to a more algebraic definition. An ellipse is the set of points, and the conic sections have many properties. You could spend days and weeks studying the properties with calculus, with reflection properties. They are truly, truly unique. And you may already know about these from your high school physics or whatever, but the conic sections and the quadric surfaces, the ellipsoids, the paraboloids, the hyperboloids, they're remarkable. So an ellipse is the set of points in the plane. The sum of whose distances, this is interesting, the sum of whose distances from two fixed points is a positive constant. So this indeed is a little bit, well, we're thinking, you're thinking, was this more complicated than the parabola? Not really. The parabola is probably more complicated than the ellipse because, that P gives you the focus and the directrix, and you open up, left, downward, left, right, upward, downward. The ellipse is going to be more like the circle, so we're going to think it's going to have like a center, like a vertex, a center, even though it may not be completely circle-like. And X and Y intercepts maybe, so the circles and ellipses can't seem to be as complicated as the parabola. But in order to get some type of understanding here, we're going to talk about two fixed points as being foci, one focus and a second focus, plural foci. So we're going to call these, for instance, we're going to take C to be a positive real number, just like kind of like before we weren't worrying that P was positive, it can be negative. But here we're going to take C to be positive, and we're going to define two foci. One's going to be, and we're going to start on the x-axis, and then of course we could flip these to the y and do the same thing we did before. So we're going to look at a focus as being a point on the x-axis, focus 1, and also focus 2 that are equidistant from each other to keep the algebra simple. So we're going to call this focus 2, and that's going to be C0. So again, you're thinking, well, this is a lot of convention. We just have two fixed points. Okay, so if they're fixed, let's just set them up on the axis so that well, of course, they're going to have a certain distance from them. But basically what I'm saying is that we've set these up so that they're equidistant from the origin. Of course, the distance between them is fixed. So we're thinking, how can we make this really, really simple? We thought, well, we'll get a point on the parabola that's the origin, and we'll set up the focus and the directrix so we know that 0, 0 is on the parabola. Here we're thinking, okay, we're just going to call the two fixed points this that are situated on the x-axis equidistant from the origin. We can do it. Why not? We don't lose any generality. We just make it easier to make an algebraic manifestation of this. Now, for this positive constant, just like this is a convention, so I'll just say fix C positive, and now we want to fix A positive. So fix C positive and A positive, and we'll take the positive constant, so define positive constant as 2A. Let me write that so you can read it. Constant as 2A. Now this turns out to be a little bit more user-friendly with algebra. Again, this didn't come up overnight, but when you try to find nice user-friendly equations, math is all about that. And when they're not very user-friendly, it's not because the effort wasn't there. So we're going to take that positive constant to be 2A, and we're going to take the foci to be situated this way. So this is going to make a very simple geometry once we finish this. So let's write this down. So let's just go ahead and do it. We'll just say, okay, we'll put the focus here. So focus 2, C comma 0. And then equidistant from the origin, about right here, will be focus 1. Yeah, I could a little bit. There we go. And so now we're thinking, okay, well, the sum of whose distances, all the set of points in the plane, the sum of whose distances from 2 fixed points is a positive constant. So we're thinking, you know, if we had this point on the ellipse, this is why we use the 2a. We'll think, okay, this is just a isosceles triangle. And so this would have to be A, and this would have to be A, the sum of whose distances from 2 fixed points is 2A. So now you see why this is useful. And so then you're thinking, all right, well, here we go. That means now that 2A is bigger than 2C. So with this setup, 2A is bigger than 2C. Equivalently, A in this case would be bigger than C, just by our convention. That's very important. So if we set up this convention this way, and the definition is satisfied, if we take a very convenient point, we know that point's on the ellipse, and that's actually going to create this oval that we think about as we generate additional points. But we don't have to guess about that. The algebra will basically generate that particular curve for us. So now we're thinking, okay, how do we write this in a way that we satisfy the definition and then get some algebra? So we do it the same way. In this case, we'll call this, we'll just take any old point here. Let's just say, you know, as we continue to generate this thing, or something like that, we'll take a point right here. So let P be any point on the ellipse. Something like that. And of course, it'd be going this way too. So we're just kind of thinking outside the box. So if P, X, Y is any point on the ellipse, we can do the same thing we did before. Think about the distances from the 2 fixed points. Now here, of course, we can't really do the squares because it's a more complicated setup. So I'm going to do as much abstract work. We work together to make the equation as simple. Then we'll substitute all the values in and see where that gets us. So now, if we think, okay, so the distance between P and F1 plus the distance between P and F2 must be 2A. So let's write that down. So the distance between P and F1, so make that into a P, P and F1 plus the distance between P and F2 must be equal to 2A, okay? Now, what I want to do is these have radicals in them, and we will eventually do the difference between the coordinates and square them, but let's just go ahead and make this as simple as we can and then fill in those numbers. So now notice we could isolate one of these. So I think what I did here, and it doesn't matter, we can do this. I change up this derivation every time I do it, because that's just the nature of being a math professor. You want to think of what's the simplest way to do this that gets the point across. So you can avoid doing all the substitution until a stage that make sense and then cut down on the amount of work. So now we have 2a minus the distance between P and F2. So again, we're thinking, okay, so this has a radical in it, and so we can square to get rid of the radical, then substitute. So first what we're going to do is square to remove radical. Because if we square it, we know the radical's gone. So this is going to be a symbolic computation. Then we'll fill everything in. So now what's that going to give us? This will be the square of the distance, square each side between P and F, and square this side. So square that. Then do the product times 2. So that's minus a 4a times the distance between P and F2 plus the square of this distance. So that gets rid of that radical. But that one still survives, so we're kind of sunk. But that's okay, we'll be good. So the distance squared F2. Now what I did here is I'm thinking, okay, so at this point, the only place that there's a radical is right there. So let's isolate that, put everything on one side, and then we can substitute everything in square and see how it simplifies. Okay, so now put in your notes, just say isolate. Isolate. Just like we were doing college algebra, isolate and square. We're doing the same thing here. So now we'll have 4, bring this over to the left, 4a times the distance between P and F2 equals, and so take everything over, leave these two where they are, 4a squared plus the distance squared between P and F2 minus the distance, take this over, the distance squared P F1. Now, we're at the best stage here to substitute. We didn't want to substitute too soon because that would have been a complete waste of time. But this is getting kind of complicated here. So what the key is that we're hoping, keeping our fingers crossed, that most of these terms will absorb, and they will. So now substitute. So let's do this. So we have 4a, we got the bracket. So we're going to do the distance between P and F2. So P and F2 in this particular case, notice, and I think when you look at this and you think about how we've written this, it's very simple. So we'll do P and F2. So we'll do x minus c, quantity squared. And then we'll do y minus 0, which is just y, quantity squared. That'll be to the 1/2. So again, P and F2, the distance between, the difference between the x coordinates, x minus c squared plus y minus 0 squared. And of course, that still has the radical on it, times 4a. Now go over here, 4a squared, it's fixed. Now we want to square. So notice here, this is going to be the same thing. This is just going to be the P and the F2 that we have here. So this will be repeated. So let's just write the same thing down without the radical. X minus c, quantity squared, plus y squared. That's just like this right over here without the radical because it's squared, see? And then here minus, so we need to use our brackets, P and F1. So we'll do x minus the negative. So this is x plus c, quantity squared. And then y minus 0, so that's plus y squared, okay? So that was not hard at all. We've done this many times, but now you're seeing that this was a better time to substitute instead of up here and getting all those letters hanging out and making a million mistakes. So now we just wait until we got it into a really nice form. Now notice we can reduce some things and hopefully we can divide through by 4 or something. So let's write this down and expand this. So 4a, and we can go ahead and write this out if you like. This will be x squared minus 2xc plus c squared plus y squared to the 1/2. Okay, so that's just expanding these terms. Negative 2xc, x squared plus c squared equals 4a squared. Now expand all of this. We know what that's going to be. Plus x squared minus 2xc plus c squared. Okay, and now minus, go ahead and expand all of this, then we'll distribute x squared plus 2xc plus c squared plus y squared. So we're doing a lot of court reporting, but that's okay. So we have 4a, so just repeat this side, x squared minus 2xc plus c squared plus y squared to the 1/2. Now we want to combine all of these things. So notice we have the minus here. So let me go ahead and write it out. Let me write it out, and then that way you won't have to guess. This way it'll be much clearer. Distribute the negative, so we get negative x squared minus 2xc minus c squared minus y squared. And let's see here. I left out my y squared right here, so I'll stick that in. Let me just put that y squared down here. I expanded this, so I'll just put this down here. And that's going to absorb that one. So there we go. So remember, when we good court reporters, that I just moved that down there since I didn't write it right here. So put that there, and there we go. So absorb x squares, absorb c squares, absorb, and all we're left with is a negative 4xc and a 4a squared. So here, remember, I just kind of moved this guy down to here. So very good. The math always tells us what to do. I had a student one time say, "Why do you always say that? It's not speaking to me." I said, "Well, it will if you look at it. The math speaks to you. It's like you left that out, so put it in." Okay, so now we get 4a squared minus 4c times an x. Well, I guess I'm writing it xc, so I'll just put it xc then, right here. And now notice the 4 is absorbed. Is absorbed, they're gone. So we get a x squared minus 2xc plus c squared plus y squared, the 1 equals a squared minus xc. So now what we can do here is square both sides to get rid of the last radical. So square again. Now, like I said before, I'll put in a whole lot of extra steps here to make it simple, and it's good, and that's the way you need to do it. You can leave out some of the steps, but it's best to put them in. So now when we square, we get a squared, and now all this radical's gone. This radical goes, so that gives us an a squared times an x squared minus a 2a squared xc plus a squared times c squared plus a squared times y squared. Note what I did here. When we square it, the radical goes away and the a gets squared. So a squared times x squared, a squared times negative 2xc, right there. A squared times c squared, a squared times y squared equals a squared minus xc. Now we can put everything together. Now I think in this particular case, let's see, I've got, oh, and over here, let me square this. square this too. So we get a to the fourth minus 2a squared xc. I want it to be over, so I jump the gun. X squared c squared. So don't jump the gun. So now these absorb. Almost done. I promise you the result will be what you think it is. But this is important. This is what you do in calculus. You never shy away from the algebra because the algebra is how you do the calculus. So notice we're left, we want to get all of our x's and our y's on one side and the riffraff on the other, and keep our fingers crossed that it's going to look like a circle. So now we've got this dude here. So we've got, let's put all the x's together, a squared x squared. And over here we've got a x squared, so we're going to take that over. So this is going to be minus c squared times x squared. I'll write it that way. So as we do them, just put a little check, taking care of that, taking care of that. And now the y squared, we just leave, it's right there. So we'll take care of that, plus a squared y squared. So put a check there. And now take this over to join this dude. So let's take this one over to join that guy. So we have equals a to the fourth minus a squared c squared. So now we can get all of our x's together. So x squared times a squared minus c squared plus a squared y squared equals, now factor the a squared minus c squared. Now remember, and I guess I kind of lucked up a little bit here, because now remember, excuse me, running in that cold weather, we have a is greater than c. We determined that from our construction. So this is good. That's a positive number. So let's divide both sides by this. So we'll divide a squared minus c squared. I'll do what you all do. This is what you all do. I never do this. I feel like I'm in high school doing the division process. There we go. Very good. I always don't do this, so I thought I've been inspired. So now notice the a squared minus c squared absorbs, so we get x squared over a squared plus the a squared is absorbed, y squared, a squared minus c squared, and of course that's a 1. Now this is good, and this is where we make a notation change. This is a positive number by construction. So what we do is we set b squared equal to a squared minus c squared. And this is going to help us define c, the focus. So flip them. So c squared will always be equal to a squared minus b squared, which is a positive number. And so the larger denominator will always correspond to the variable that contains the particular foci. So that here, if this is the larger one, which it is, the foci are on the horizontal axis or x-axis. So that's, the convention is actually proving to be very useful. So now we get our standard equation, x squared over a squared plus y squared over b squared equals 1. And so now that looks just like a circle. And of course, a is equal to b, that is a circle. That's the unit circle. I mean, well, if they're 1, obviously. But the thing is that this is what we expected. If we have a conic section, as we had from the very beginning, if we have a conic section, we could orient this in a way so that, again, it's perpendicular to the axis of the cone, and this would actually be a circle. So we need that possibility. So now what we see is this equation allows for that. because if A is equal to B, this is the equation of a circle. So we look at the ellipse as being a more generalized closed curve. Notice the parabola is not closed. This curve is closed. We already know about circles, and so we're like, yay, because this is what we expected. So now let's just go ahead and summarize. We've got this guy right here, which defines the foci. So if you have the a squared and the b squared, you always take the larger denominator minus the smaller to get c squared, and that helps you find the foci. So let's write it down. Here's the summary. C squared, I'll write it again, a squared minus b squared. So this is the standard form, just like doing the y squared equals 4px. So you can figure out the p. You write this with the standard form with the 1, so you can figure out the a squared and the b squared. So again, the a squared will always correspond to the larger denominator. So a squared, larger denominator. That's how we've constructed this. And then we're going to have the foci. Focus 1 will be negative C0, or you can just do plus or minus. I call them focus 1, focus 2. I guess it doesn't matter. C0. And then we're going to define the vertices to be the endpoints, the x-intercepts or y-intercepts, wherever the foci are. So we're going to say that the vertices will be negative a comma 0. In this case, that would be x-intercepts. And vertex 2 will be positive a 0. So a lot of times, Dr. Stewart will just do foci plus or minus c, vertices plus or minus a. And then, like I said before, the way we've done the symmetry and all that, this will correspond to the major axis, and then we'll have the minor axis. And then we'll have length, and I'll write this down. The length of the major will be 2a, and the length of the minor will be 2b. And so now when we think of this, we've got the picture that we thought was going to be the case. The algebra has verified the oval shape. And of course, the a is bigger than the c, so the intercepts are outside of where the foci are. So now we've got our standard picture of the ellipse. And then of course we can switch the x and the y like we did with the parabola. So now what we see is we have the b and the minus b, which would just be the y-intercepts in this case. We have the foci. And then we have the vertices. So remember, the vertices will always correspond to the major axis or the longer axis. And that's always going to correspond to the denominator that's larger. So if the larger denominator is involved with the x squared, that's where you find your a squared. If it's larger with the y squared, then you're going to have your foci distributed on the vertical axis. So this convention is very useful, but you have to remember how we've set this up and abide by that, just like the conventions that we set up with trigonometry. It's the same thing. So now what we can see is that we don't really have special names for the b and the minus b. We just know that these are the y-intercepts, but we do have special names here. And then of course the foci. So this is not very complicated. You're thinking this makes for a quick graph, because once you have, I mean, you can figure out the foci, but if you've got the x-intercepts, the y-intercepts, figure out a and b, and then you can easily do a quick sketch like you do for a circle. So just remember the way we've set this up: a is positive, b is positive, and c is positive. So when we think of square roots, we don't have to pretty much do plus or minus. By definition, these are positive quantities. So when we write 2a and 2b for the length, we are presupposing that we have defined these to be positive, and they are, because they represent distances. So the distance b here, the distance a here, the distance c here. So you don't have to get real picky about pluses and minuses when you're doing this, unless you're just going to look at a particular arc of the ellipse. Notice, like a circle, this is not a function. The upper arc defines a function and the lower arc defines a function. Okay, so at least now what we're seeing is that just like the parabola, it's the quadratic functions we've been working with. Just like the circle, or just when and then when we think about the ellipse, that just reminds us of the circle. So everything's connected here so far. The hyperbolas are kind of off into their own. They're a quirky group and very, very unusual. And we'll talk about that on Thursday. But let's just do a couple of examples of this. So now we have a nice little summary of this. And of course, you can flip all this around for the y-axis situation. So let's write that down and then do a couple of examples. So of course, we can flip the x and the y. So switch x and y. We don't have to start over. We don't want to do that. So we're going to get, our equation will be y squared over a squared plus x squared over b squared equals 1. And so now the foci, the x's and y's flip. So we'll have focus 1 will be 0, negative c. Focus 2 will be 0, positive c. Vertex 1 will be 0, negative a. And vertex 2 will be 0, positive a. And then, of course, we still have c squared equals a squared minus b squared. And then, of course, the major and minor length. So major has the same length, major of length 2a, minor of length 2b. So again, and if we do this, we'll just situate it this way. So we could have started out and done our derivation just like we could have done it with the parabola, to have the foci situated on the y-axis. And it doesn't matter. So we got our a and our negative a, and our b and our negative b. So here's our situation there. And then, of course, we'll have our foci. So we have here vertex 2, 0a, vertex 1, 0, negative a, b, negative b, focus 2, 0, c, focus 1, 0, negative c. So we don't have to start over. It's just that now the larger denominator is associated with the y variable. And so then the foci would necessarily be distributed on the vertical axis. So it's like when we do our derivation, we could have just taken this picture and done it this way. So the thing is that we do the work once and then we don't do it again. So again, just like with the parabola, we just switch things out and get a twofer, so to speak. So there we go. Done with that. Now let's look at a couple of examples. So here's an example. So let's do a clean sheet. So with this, again, we just do the particulars. Again, this is easy. You'll like this work. It's not hard. It's not nearly as hard as trigonometry. So it's a nice breather. But you do have to spend a little, well, not a little bit, but a lot of time on it to get used to it. So here, what we want to do is for instance, vertices, foci. Oh, and I need to define eccentricity. Eccentricity. And I'll do that right now. Eccentricity is just basically a shape operator. And then we'll do this example. This is another piece of the puzzle, kind of like the focal diameter. So this is the counterpart to the focal diameter. We define eccentricity E to be C over A. Now, why is that any good? It kind of lets us know, is the shape more like a circle or is the shape more like an oval? So again, if we think about this, we can write this as the square root of C squared. Now, C squared is A squared minus B squared. So let's write it this way. So we'll do square root, well, here, let me do this. We'll write this as A squared minus B squared. So the square root of C squared is the absolute value of C, but C is positive, so that's C. And then we'll write A as the square root of A squared. Okay, so we're just using the definition or conventions that we set up. And so now what is this? Divide by A, and you just get the square root of 1 minus B over A quantity squared. So divide by A, then you get B squared over A squared, which you can write it with the laws of exponents. So now what we're seeing is that if A and B are relatively close together, we're thinking more circle-like. And so, for instance, we'll just say if A is close to B, it can't be smaller, but maybe just approximately the same, then this will imply that we just basically get 1 minus 1 here because they're close to the same. So we'll get a number a little bit bigger than 1 under here. So we'll say eccentricity is closer to 0. So it's small. We'll just say small. In the sense, by definition, we see that eccentricity will be between 0 and 1 by definition. And so then we would say, if that's the case, we're thinking circle. We're like a circle. And then, of course, if A is a lot bigger than B, A is a lot bigger, then we're thinking that contribution will be smaller. So we're not subtracting so much from 1. So we'll say E is closer to 1. And basically here we get oval. So with A and B being closer in magnitude, we're thinking the ellipse will have more of a circle shape. If A is a lot bigger than B, or noticeably bigger, then we'll expect the oval shape. So the idea here is that this is just a way of and again, WebAssign will just say, what's the eccentricity? And so what I would do is just always think of it like this, so you can kind of figure this out. So if it's closer to 0, then it is, we're thinking circle. If it's closer to 1, then we'll think oval. And if it's somewhere in between, it's kind of hard to tell. It just really depends how you sketch your ellipse and the scales that you use. But this is just a little extra thing, not overly important, but in physics classes, they like to mention this in curve theory and things like that. So that's eccentricity, C over A. So that's just a little extra piece there. Okay, interesting, right? This never stops. So let's go back to the problem. So say we had some, as you can already see, the ellipses are easier than the parabolas, just a lot easier, like circles. So we want eccentricity, foci, and vertices. And so this will be, here's what we're given, 2x squared plus 25y squared equals 50. So now remember the whole idea is something like this. Maybe we get this, or maybe the x's and the y's are reversed. Is something like this. So that's kind of the goal here. And remember, c squared equals a squared minus b squared, always. So when we look at this, we're thinking, well, this doesn't look like this, so let's divide by 50 to get the 1. So we get 2x squared over 50 plus 25y squared over 50 equals 1. Well, let me just write it out. That way you see 50 over 50, right? So what does that give us? Well, 2 into 50 is 25. So that gives us x squared over 25. Excuse me. And then 25 into 50 is 2. So this gives us y squared over 2 equals 1. That's a standard form. And now, of course, the larger denominator is associated with the x variable. So we know that the foci will be on the horizontal axis. I say horizontal because if we translate things, the axis will be horizontal, not necessarily the x-axis. So now we have what? A squared equals 25, b squared equals 2. So this implies c squared equals what? 25 minus 2, which is 23. I mean, this is so easy. Trigonometry is much more challenging and much more abstract. This is just so nice and so useful, ladies and gentlemen. The conic sections come up all the time. So you, just like knowing the trig, you got your conic sections down, you're ready for calculus. So now we have A equals 5, B equals the principal square root of 2, and C is this number 23, square root. Okay, so of course the major, we'll just go ahead and knock it off. The major will have length that I'll just say, when I say major, I'm just going to refer to its length. So the major will be 2 times 5, which is 10. The minor will just be 2 times the square root of 2, and we're done. So the major axis has length 10, the minor axis has length 2 root 2, and then this will help us find the foci. So the vertices, we can do vertex 1 will be -5, comma 0. Vertex 2 will be 5, comma 0. Focus 1 will be negative root 23, 0. So that's close to that. And then focus 2 will be square root 23, 0. And be sure to use your WebAssign. You'll write these as ordered pairs, and they'll say smaller number, larger number to get the order right. Don't disregard the formatting and just mess it up. I mean, by now you should be experts with this. And like I say, take your time and do your math every day. Do your math every day. Do not wait 3 or 4 days to do math and then get frustrated because you don't understand it. Do math every day. This is not something that you need to forsake at this time in the semester. Okay, I expect you to be responsible about this class. Now we're thinking, okay, so what's left? Eccentricity. And we're thinking, well, no big deal. So we have square root c over a. So this will be the square root of 23 divided by 5. So, square root 23, a little bit less than 5. So we expect this to be more circular in shape. So we're thinking circle shape. But again, that's just a little aside, no big deal, no big deal. So if you do a little simple sketch, I mean, that's all we have to do, just a simple sketch. Thinking about graphing the trig functions and all the work we have to do, this is certainly easier. And we like it. So now if you want, we can just go ahead and mark off the 5, just your own little scale here. Just kind of approximate the scale, just to get a nice drawing, so to speak. Root 2, so we'll be, let's see here. So now, oh, well, sorry. oval. Let me go back here, closer to 1, oval. So the math tells Professor Ron oval, not circle, oval. So now, of course, right here about, root 2, just kind of approximate. So we've got root 2, negative root 2. Right there. And so we can connect. So there's our nice oval-like ellipse. And then, of course, if you like, real close here, just kind of, little bit of liberty here. So I'll label these. And so here, focus 2. Oh, wrong place. Closer to the other ones. So about right here. Let me do that in red. Now I'm glad I did it in red. It said, Professor Ron. There we go. All right there. About right here. So we have focus 2, square root 23, 0, and focus 1. Right there. So this is a lot easier. And of course, if you don't make silly mistakes. But the thing about this is that when we think about the ellipse, we're like so comforted in the fact that it's so much like the circle, and we just get generalized circles, so to speak, where the a squared and the b squared have their own values, but they are all abiding by this convention here. So even though this is simple, we must abide by the convention. And of course, if the larger denominator associated with the x squared, I need to make sure I type these on the x-axis. So this is good. Again, when you look for your sketch, you determine this already. So when you start to plot, wait a minute, these are on the x-axis, put them here, and then you've got a nice sketch and you're good to go. Now, let's look at an example where we use this, where they give us some information. Let's see here. Let's see, here's a good one. Let's try this one. Let's just change it up a little bit. So now you can see that standard form, read it off. Standard form, read it off. So let's look at an example here where they give us some information. So here's an example. So we're given that the foci, and this is how Dr. Stewart will give them to you a lot of times, ladies and gentlemen. They'll give you the plus or minus. So I'll just kind of do that, plus or minus root 10. So that's situated on the x-axis. And then we have the vertices, plus or minus 8, 0. So now when you look at this, what they say in this particular case, I think it wrote determine equation of ellipse. Now, notice here that by definition, we just write down what these are. This is plus or minus c, 0, and the vertices are plus or minus a, 0. So now what we see is that the major axis is associated with the horizontal axis. So this implies, now we've got c is the square root of 10, a is 8, which implies a squared is 64, or 8 squared, and c squared is equal to 10. So now we've got this. So we know c squared equals a squared minus b squared, if and only if b squared equals a squared minus c squared. So we know this to be true, then transpose. And so we get 64 minus 10, which is 54. So again, this is the smaller denominator, which will now be associated with y squared because we have that the association with the x squared is the major axis. So this implies that we have x squared over 64 a squared plus y squared over 54 b squared equals 1. So even though these are simple equations and these are simple problems, we have to abide by the convention, and that's what this is good for. You look at these examples and you think, oh, I see. I just have to make sure that I'm abiding by the convention of our construction. So just like we go back to the unit circle, we have to go back to our construction process. Now, here's one more example I want to do. I thought this was interesting. A nice equation. We'll close with this. This flows in. Dr. Stewart always comes up with these really interesting problems. So we have example. So we have the eccentricity is 1/4, and we have the foci are plus or minus 3/4 over 0. And notice here, and this is how I want to actually do this. We can actually solve for b squared and get this done. So notice here. This implies c equals 3/4 and 1/4 equals what? What do we have? C over A, right? So now if and only if you multiply this out, we have A is equal to 4C. So if you multiply through by 4, we get 4C, cross multiply by A is equal to 4C. So we get what? 4 times 3/4. A is equal to what? 3. So we look at that and say, well, that's good. And now we need B, but now we know C squared equals A squared minus B squared. If I do these problems a million different ways, it's just how you look at the equations. So B squared will be A squared minus C squared. So now we've got what? A squared is 9, square 3. Then C squared is 9 over 16, right? So 9 divided by 16. So this gives us 9 times 16 minus 9 over 16. How interesting. So if you like, what is this? This is 9 times 15 over 16. Just factor that. I factor everything. So that's what, a 5 and a 4. 4 plus 9, 135. How fascinating. So now there's b squared. So even though this problem's not terribly interesting, it just involves the construction process. We defined eccentricity as c over a. So when I looked up and I said, well, what is this? Oh, it's c over a. So that allows us to find a. And then we know that c squared is always equal to a squared minus b squared by our convention, by our construction process. So now we get what? What does this imply? A squared we know is 9. So this implies a squared equals 9 right there. So we have what? So now what's the larger? What's larger now? What's bigger in this case? 9 or this? Well, if we divide this by 16, which is bigger? Well, let's just look at this. We know we don't even have to, we know this is smaller because we know that these are situated on the x-axis. So that solves it for us. I'll defer to that. So we get x squared over 9 plus y squared divided by 135 over 16 equals 1. Now, of course, this is a little bit obtuse, so you can flip it, even though this is standard form here. Equivalently, we have x squared over 9 plus, flip it, 16y squared over 135. equals 1. So again, I didn't really have to look at this. I know that this is smaller than 9 because of the construction process. We see that the foci are distributed on the horizontal axis. So we know that this is larger, and you can just see that it is. But you wouldn't even have to do that by the given. So again, these are just kind of fun little problems. They're not like the linchpin of your existence. You don't get into calculus and they say, okay, what's the equation of this ellipse? That's not how it's going to happen. You're going to see an equation of an ellipse, and you're going to have to work with it algebraically like we've done. But this type of computation is just good practice for solving word problems, or putting ideas together, just like we've done here in a very simple process, utilizing the construction process that we've set up. So when we go back, just in summary here, when we go back to how it all started, these are the conventions that we set up. We set up that A is positive and C is positive, and then by this convention, we have that A is bigger than C. And then to finish off everything, we have the C squared is always equal to A squared minus B squared, because we define B squared to be A squared minus C squared. So all of this, just like the parabola, is based on convention, okay? Now, this wasn't thought about overnight, but through the genius of Rene Descartes, we've made all of the elegant findings of the Greeks into an algebraic construct. That is, that's what we call analytic geometry. We take the geometry and coordinatize it. So now, when we look at these problems, this ellipse has this algebraic form, just like a circle has an algebraic form. Now we see a parabola has an algebraic form. And then, of course, on Thursday, we'll see that the hyperbola has an algebraic form. So for the for the fourth test, we'll just cover through the material that we've done today. What we do on Thursday won't be covered. So I'll stop with the material today. And basically, this test will just be the remaining trig information that we had, and just the introductory material on the parabolas and the ellipses, which, of course, as you see, is very simple. So now what I want you to do is clean up your trigonometry. If you come to office hours, conference hours, if you like. If otherwise, I'll see you on Thursday. And make sure that you have your note cards, that you got everything dressed up in a way. Do the same with the ellipse and the parabola. Get everything coordinated so you have the ideas that we've set up. You don't really memorize all of this so much as you know it because you've used it. But when you're taking a test, you can use the formula sheet on Blackboard, and you can make your own. And that way you don't have to, put yourself in jeopardy because you confuse something. So the beauty of the ellipses and the parabolas is they're very straightforward, not nearly as abstract as the trigonometry. So enjoy that. Again, thank you for your attendance this morning. I hope you're enjoying a nice break into something interesting. Stay warm. I love the cool weather, but with my Dr. Fieldhead, I have to always wrap up when I go outside. So you all have a good day. And if I don't see you at my conference hours, I'll see you on Thursday. Take care, everybody.
Have a good day, sir.
Have a
Bye.
Thank you.
Thanks,
Have a good day.
everyone.
See you.
Bye.